All right, Unit 8 deals with trigonometry. Trigonometry is a fancy word that just means right triangle geometry. So a lot of good stuff happening here. We're going to focus initially here on right triangles, the Pythagorean theorem, and of course some special right triangles in the mix. In order to use that Pythagorean theorem, establish these relationships, we have to have a calculator and we have to know how to simplify radicals. We will prove the Pythagorean theorem using similar right triangles like we did in lesson 7.4. So scroll back to that video if you'd like to see how that awesomeness works. And then we're going to do some special right triangles using the Pythagorean theorem to sort of shortcut our work. The goal here is that if we know our right triangle rules, it will make things go a little bit quicker for us. Obviously, if you don't learn our right triangle rules, you can just focus on what you already know from your previous classes with the Pythagorean theorem, and that will do the trick. So the Pythagorean theorem, you know this already. You know that given a right triangle, and you don't have to write all this down, but if you write this and draw the picture, that should be good, that if you have a right triangle with sides A, B, and C, that the sum of the squares of the lengths of the legs is equal to the length of the hypotenuse squared, all right? And so that is obviously not new information, but the why is it true is sometimes obviously in question. So what we want to be able to do is use this notion of our three similar right triangles like we drew in lesson 7.4. And so what I'd like for you to do is draw these right triangles. Let me see if I can do a better job of drawing those right triangles, small, medium, and large. Obviously, you want to mark up the single and the double marked angles, which means that this is a single and a double marked angle. We're going to have our doubles and our singles along with our right angles in our divided triangles. So we'll want to make sure that in our very big triangle, opposite from the single marked, we have A. Opposite from the double marked, we've got B. And of course, the hypotenuse is C. C is the same as E and F added together, but here we're going to call it C. In this triangle, this medium-sized triangle, I guess, across from the single marked angle, I've got D. Across from the right angle, I've got B. And across from the double marked angle, I've got F. And then in this situation right here with this right angle, the hypotenuse there is A, across from the single marked angle is E, and across from the double marked angle is D. This should allow us to create some proportions, and I've conveniently got those typed here. So we know that comparing in the big triangle to the little triangle, or little triangle to big triangle, A over C is the same as E over A, right? And here we know that, that B over C, comparing hypotenuses, is the same as F over B, comparing those long legs. And so we have these two separate equations, these two separate proportions, using double A's and double B's, because what I want to show is when I cross multiply and I get A squared, I'm going to get E times C. And when I get B squared, I'm going to get F times C, that product of those side lengths, all right? So this really isn't the issue here, but what I want to make sure that we have is that we've got A squared and B squared. Now when I add A squared and B squared, I get CE and CF. And if I factor out that C, I have C times E plus F. And we know that E plus F is the length of that hypotenuse C. E plus F is the same as C. So now I have C times C, or C squared. So here is just an exploration of and a proof of that Pythagorean theorem. This is the explanation for why that works. All right? Now you already trusted and already believed that A squared plus B squared equals C squared. And so if this is a stretch in your understanding, please see me with that question. But what we want to be able to do with the Pythagorean theorem is use it. So obviously you've already done this before in your previous math classes, so this should not be a struggle. However, we are going to make sure that we can simplify radicals as we go. We want to write in simplest radical form, so our square roots are going to need to be simplified, written in their lowest form. We are always going to, and you're going to hate this if you are annoyed by having to write down formulas, but you're going to get to write down your formula every time. We're going to have 20 squared plus 21 squared is equal to x squared. One thing to be reminded of is that it doesn't matter which one is A and which one is B, but it absolutely matters which one is the hypotenuse. All right, the hypotenuse is always C. The hypotenuse is always C. So you have to be able to identify where the hypotenuse goes. A and B, if you square B and then add it to A squared, if I did 21 squared plus 20 squared, that's the same as 20 squared plus 21 squared. So if I change the order, it doesn't change the sum over here. But if I have the wrong thing in the wrong side of the equation, that messes things up. Generally, here's a good rule of thumb. The smaller side is A, the longer side is B, the hypotenuse is C. The smaller side is A, the longer side is B, I said side, but legs. And then the hypotenuse is always the longest side of the triangle, opposite from the right angle, and so that will always be C. It doesn't matter though. If you get A and B mixed up, that is not an issue. It doesn't change our sums. All right? Now you might not know your perfect squares there, and that is totally okay. 20 squared is 400, and 21 squared is 441. All right, let me double check that. 21 squared. Great, 441. Now when I add those together, you might want to use a calculator. You might be able to do that without any challenge. But we get this 841 that we then have to take the square root of. And our job here is to do simplest radical form, so let's pray to the calculator gods that this is a perfect square, that this is a perfect square to find out that the length of the hypotenuse is 29. That works out perfectly. That's nice. When we take the square root of 841, it gives us 29, so that works out nice and fancy pants. All right, if we had to simplify that square root, we'd have to do, obviously, some work. That's a pretty large sum there. We're going to write down our formula every single time. If you're not writing down your formula every time, things are not going to go well for us in this unit. I want things to go really well for you in this unit. So we are going to do that work as well as we can to make sure that we can address your situations with being able to write formulas, substitute in values, and go from there. If we establish the habit when it's easy to write out the formulas, then you will write out the formulas when it's a little more difficult of an exercise. So here we have 336, and we have to take the square root of 336. So I'm gonna mess with this and say, is it divisible by 4? Yes, it is. It looks like it gives us 84, so that means it's gonna be divisible by 4 times 4. And it is. So this gives us z is equal to the square root of 16 and the square root of 21. I just did some trial and error. You can obviously do factor trees and put them in all kinds of other garbage, whatever it is that you guys do to make sure that you simplify square roots correctly. And we get 4 times the square root of 21 is equal to z. To find y here, we're going to have a squared and b squared equals c squared. Write down your formula if you're wanting full credit here and in life. So we want to make sure that we do a good job with that. And we are going to do some subtraction. This is not, again, too terribly difficult to do that subtraction. Use your brain, use your calculator, and then we have to take the square root of 112. Let's find out what perfect square factors that has. I know that it does divide by 4. It looks like it divides by another 4. So we have another factor of 16 and 7 in this case. So that means that y is equal to 4 times the square root of 7. When it comes to simplifying those square roots, obviously you've got to be able to do that in this unit. If you're having trouble with the Algebra 1 there, you can visit with me. You can do some practice on IXL. You can check out Khan Academy. You can check out the video that I posted a couple weeks ago. You can do all of that. Actually, I didn't post a new video. I used my video from years ago. You can check out my video from years ago. The math hasn't changed on how to simplify square roots, whether you're in Algebra 1, whether you're in geometry, or whether you're going to be in Algebra 2 or Honors Algebra 2 next year. You need to know how to simplify square roots if you want to be successful on that. If you're needing additional assistance, obviously see me, take care of yourself on that to make sure that you can do the things. All right, so the converse of the Pythagorean theorem is also true, and that says that, hey, if a squared plus b squared equals c squared, then our triangle is a right triangle. So if we can show that c squared equals a squared and b squared, then we do indeed have a right triangle. And there's some extensions on that that are also pretty cool. Does c squared equal a squared and b squared? Now we don't know if this is a right angle, all right? We don't know, it looks like it, but we don't know that it is a right angle. So we're going to show that that angle is a right angle by putting these in order from largest, longest side to smallest side. The question is, does it equal the other two sides squared and added together? So this is going to require a little bit of work. Does c squared equal a squared and b squared? All right, do we know that that's the case? And you can check that using the calculator. If the answer is yes, they're equal each other, then yes, it's a right triangle. If they do not, Does c squared equal a squared and b squared? Does 7 squared equal 4 squared plus 6 squared? When you ask that question, you should be able to answer definitively yes or no. Now, you might not know what 85 squared is, but your calculator can multiply that. You do not need to spend time doing long multiplication to draw that out. Let your calculator do that work. 84 squared, whoops, is going to give us 7056. 13 squared, we know from our times tables, is 169. So when we add those together, we get that these are in fact equal. So yes, this is a right triangle. All right, this is a right triangle because c squared equals a squared plus b squared. Over here, does 49 equal 16 and 36? Does 49 equal 52? And the answer there, obviously 49 does not equal 52, and therefore this is not a right triangle. All right, and so if it's not a right triangle, then a squared plus b squared won't equal c squared. If it is a right triangle, then a squared plus b squared equals c squared. If c squared equals a and b squared, a squared plus b squared, then yes, it is a right triangle. If c squared does not equal a squared plus b squared, then it is not a right triangle. This is basically just a check to see if that's true. That's the converse of the Pythagorean theorem. And we might ask that question differently. What would this leg have to be for this to be a right triangle? That's a different way to ask that same question of whether or not this thing is a right triangle. All right. Put a break in the notes right there, because right now we are going to start talking about special right triangles. All right? And when I say special right triangles, I mean we're going to sort of shortcut our work with the Pythagorean theorem. Now, if you don't learn what is on these next two concepts, these extensions of the Pythagorean theorem, you can still do the Pythagorean theorem, but you're going to be doing a whole heck of a lot more work than your peers. All right? So the goal here is that if we understand this relationship, then we will expedite our work. So here, these have little s's. I would love for you to write those in cursive so that they don't look like 5s. All right, so write cursive s's if you remember how to write cursive from your elementary days. But basically, in a 45, 45, 90 triangle, this is also called an isosceles right triangle, where this and this are the same. The length of the hypotenuse is whatever the leg is times the square root of 2. That will always be the case. So, for example, if I tell you that this is 4 and this is 4 in a right triangle, that's a 45, 45, 90, it's an isosceles right triangle, you know that this has to be the length of the leg times the square root of 2. It will always be that case. If this is 15 and this is 15, then this hypotenuse is going to be 15 times the square root of 2. Does that work backwards as well? Yes. If I tell you that this is 8 square roots of 2, then what are these legs going to be? Oh, we're just going to divide by the square root of 2. Those are going to be 8. All right, so again, it's not that that's terribly difficult. There's going to be some tough division that we might have to do to divide by the square root of 2 and then rationalize denominators, all that stuff. I'm not super concerned about that because I know that you learned that really well in Algebra 1 last year and we practiced it before we got into this unit. So with that in mind, I want to make sure that we understand why this is true. Instead of using s, I'm going to use x, if that's okay. I'm going to go ahead here and say that this is x, and this is our hypotenuse. And I'm going to prove that if we know that we have a 45, 45, 90 triangle, right, an isosceles right triangle, so I'm going to put 45s in here, but we know that if this is an isosceles right triangle where the two legs are congruent, we know that these angles have to be 45 and 45, because 45 plus 45, the same angle in this isosceles triangle, same measure, has to add up with this 90 to get 180. So we know that those have to be 45. Now if I do a squared and b squared equals c squared, I can show that if I do x squared and x squared equals my hypotenuse squared, I get 2x squared is equal to c squared. To find out what c is, I have to take the square root on both sides. So when I do the square root of 2x squareds, I get the square root of x squared, that is x, and then I'm left with the square root of 2. So here is kind of an explanation or proof of why the hypotenuse is going to be x times the square root of 2. Please include that in your notes. But it shows that if I can just answer that question, I don't have to do that work of writing out our formula, substituting in my 4s to find out what my hypotenuse is going to be, So I get 16, and 16 is equal to the hypotenuse squared, so 32 is equal to the hypotenuse squared. I gotta take the square root of 32 to find out what the hypotenuse is. I gotta break that down as the square root of 16 and the square root of 2, which gives me 4 square roots of 2 as the hypotenuse. Now you can do all that work, because we've demonstrated that you can do all that work. We know how to do the Pythagorean theorem, we can find the hypotenuse, etc. So you know how to do that, but wasn't it easier for me to just write what the answer was? Like to just know that it's gonna be 4 times the square root of 2? Again, you are welcome to do that work, but I would hope that you would understand this relationship well enough that you don't have to do 1, 2, 3, 4, 5, 6, 7 steps of work. Instead, you can just be like, oh, that's 4, that's 4. This is 4 square roots of 2. Oh, this is 10, and this is 10. That means that this is going to be 10 square roots of 2. I don't have to do all of this work with 10s in there to get the square root of 200 that then I have to simplify, right? So the goal on that is to make sure that you learn this fact, this concept, so that you don't have to do a bunch of work. If you learn the concept, you don't have to do the work. If you don't learn the concept, you can do all the work. All right. Over here, when we are dealing with this other special right triangle set, 30, 60, 90 triangles, essentially what we have here is an equilateral triangle. All right? An equilateral triangle that gets cut in half. When we cut that in half, it cuts my 60-degree angle at the vertex into 30-degree angles. All right? It's perpendicular to the base, right? Because that's how that works. And it is also, we know that the angle, the vertex angle bisector in an isosceles triangle is also the perpendicular bisector of the base. We learned that in chapter 4, lesson 2. All right? So, with that in mind, when we have this 30, 60, 90 relationship, what we want to understand, and again, change that S to a cursive S. Make sure that you're writing that with a cursive S. Otherwise, that might look a little confusing to us. What we're going to show here is that when we've got that 30, 60, 90, instead of pretending that this is x, x, and x that gets cut into 1/2 x and 1/2 x, let's do these with a multiple. That way we don't have to deal with trying to square 1/2 x, 1/2 x times itself. So instead I'm going to call these 2x's, right? Because proportionally, if I just double the side lengths, I still have the same relationship. So I'm going to call these 2x's on each side. All right? So if all the sides are 2x, then that means that when I cut this part, it's going to go into x and x. So that gives me this situation, which is x, 2x. I've got my 60 degrees angle here. I've got my 30 degrees angles there, obviously not drawn to scale. And then I need to know what is this leg, all right? What is this leg? This is kind of the big question here of what is this value? Well, we can find that by doing a squared and b squared is equal to c squared. I know that x squared plus, I don't know what b is, I'm going to find it, is equal to our hypotenuse squared. Now notice how I'm taking 2x and squaring it. 2x squared is not equal to 2x squared. All right, look how that is written. These are not the same thing. All right, so we're going to talk about squaring 2x. 2x squared is the same as taking 2x's times 2x's, which is going to give you 4x squared. If we know our algebra rules, when we're taking a product to a power, we give the exponent to each of the factors. So that's 2 squared times x squared, 4x squared. So I get x squared plus b squared is equal to 4x squared, which means that b squared is equal to, let me subtract 1x squareds from both sides, 3x squareds. If I want to know what b equals, I have to take the square root on both sides. I can take the square root of x squared. I cannot take the square root of 3. So the length of this long leg is whatever that short leg was times the square root of 3. So if this is s, then this is 2s, and this is s times the square root of 3. If using s for the length of the short leg, then use x, all right? If you would rather write this than the garbage that is there, this might make a lot more sense to us. So the short leg is x, the hypotenuse is 2 times x, and the long leg is x times the square root of 3. So whatever number this is, that tells us what goes here and here. If I know this, I can divide it by 2, and then I can take this and multiply it by the square root of 3 to get that. If I have this is tough, I'd have to divide by the square root of 3 to get here, and then I have to take whatever that value is and multiply by 2 to get there. That might be a little bit more challenging to us, so let's take these rules and let's put them to work. Here we have some 45, 45, 90s. These are all going to be 45, 45, 90 examples. And we're going to understand this relationship. So if this is my right angle, this is my hypotenuse, this is the leg, this is going to equal, the hypotenuse is going to equal the leg times the square root of 2. So h in this case is going to equal to 9 times the square root of 2. I'm done. No work to do. If I write out this formula, that the hypotenuse is equal to the length of the leg times the square root of 2, then we'll be okay. If you want to write it as the length of the hypotenuse is equal to the length of the short leg, or the s times the square root of 2. Short leg, there's not a short leg and a long leg there. It's just the side in the right triangle. I generally don't want you to do that. I'd rather you understand it as the hypotenuse is equal to the length of the leg in our 45, 45, 90s times the square root of 2. Here, the hypotenuse is equal to the length of the leg times the square root of 2. So, the hypotenuse is equal to the length of our leg, which is 2 square roots of 2, times the square root of 2. If you want to see that as substitution, you can see me substitute that the leg length is 9, that the length of our leg here is 2 square roots of 2, and then we get to multiply that. That gives us 2 times the square root of 4, which is 2 times 2, which is 4. Over here, and this is the harder case, the hypotenuse is equal to the leg times the square root of 2. So in this case, I know the hypotenuse, I do not know the leg. And so I have to be able to solve this equation. If I want to get x by itself, I have to divide both sides by the square root of 2. So 16 divided by the square root of 2 is equal to x. But that is not in simplest radical form. So I have to rationalize our denominator, multiplying by the square root of 2 over the square root of 2. And that is going to give us x is equal to 16 times the square root of 2 when I multiply the numerator over the square root of 4, which means that x is equal to 8 times the square root of 2. Now sometimes, here's what's going to happen. Mr. Hibbett, I got a weird answer. I got 8 square roots of 2. Is that right? You can check it. If this is 8 times the square root of 2, then the question is, and don't check using the Pythagorean theorem, but take 8 times the square root of 2 and multiply it by the square root of 2. That's going to give us 8 times the square root of 4, which is 8 times 2, which is 16. Hey, it works. That the hypotenuse is equal to the length of the leg times the square root of 2. So you can always check those answers if that is something that you are concerned about. All right, on the next situation, we've got our 30, 60, 90 rules. Now I'm doing all of these for you. There's not anything that you're going to have to do at home. I want to make sure that you do this well. All right? So here we know that our hypotenuse is equal to 2 times the short, I'm writing in cursive, times the short leg. All right? We also know that the long leg is equal to the short leg times the square root of 3. Short leg times the square root of 3. Hypotenuse is equal to short leg times 2. So, I know the hypotenuse. I do not know the short leg, but I can solve that equation pretty quickly. 4 is equal to x. Over on this side, I now know the short leg. So now I have y is equal to x times the square root of 3. Y is equal to 4 times the square root of 3, and we're done. If we understand these relationships, which asterisk on that, make sure you have this as a formula, right? We know the relationship, we established that relationship already on the previous slide. Want to make sure that we can create those equations. In this situation, I got my 30, 60, 90. This is our hypotenuse, this is our long leg, this is our short leg. That might be a good exercise for us. We know that the hypotenuse is equal to the short leg times 2. So in this case, I know that Q is equal to the short leg times 2, so I know that Q is equal to 4. I know that the long leg is equal to the short leg times the square root of 3, so I know that P is equal to 2 times the square root of 3. Oh, that's done. Folks, this doesn't have to be difficult, but it might be for us, especially if we face this situation where we've identified the hypotenuse, the short leg, and the long leg. So if I know that the long leg is equal to the short leg times the square root of 3, then I know that 12 is equal to d times the square root of 3. Goodness, we're going to have to do some fancy work here. 12 divided by the square root of 3 is equal to d. We're going to have to rationalize that denominator. Do that work of rationalizing your denominator. All right? When you do that, you get 12 square roots of 3 over the square root of 9, which means that d is equal to 4 square roots of 3. So that's the length of our short leg. Our hypotenuse is equal to that short leg times 2. So in this case, f is equal to d times 2. Actually, you do that. I want to make sure that you can multiply those. And then we shall check. So 30, 60, 90 rules, 45, 45, 90 rules, Pythagorean theorem, its converse, all of that awesomeness. And so hopefully you will be able to apply the Pythagorean theorem to establish relationships in right triangles, use those relationships in these special right triangles to make sure that you can create these equations, solve these equations. Notice that there's not always a lot of work. Sometimes there is a little bit of work, other times it's plug and chug.